So we've talked about the way we're helping to quantify our greenhouse gas profiles through the inventory work. We've touched now on mitigation options and looking specifically at methane options. And now we're going to move on to the impact and adaptation part of climate change, because that's going to be a really important part of going forward positively into an environment that we know is changing. So the first speaker that we've got in this session is Mark Lieffering. He's actually going to talk to you about an experiment called the free Air CO2 Enrichment experiment that's been running on 20 years, and he's going to share some of those results with you.
So, thank you. Pastoral agriculture, global change, impacts and adaptations. As Tess mentioned, I'd first like to talk to you about some research we're doing on the impacts of elevated CO2 on pastures. Elevated atmospheric CO2 is arguably the most predictable of the global changes, and it's also the driver of climate change, or one of the drivers of climate change. Back to Biology 101, increased CO2 in the atmosphere usually leads to greater plant growth. So most commercial glasshouse crops, for example, they pump extra CO2 into those glasshouses to encourage the plants to grow bigger. So to study the impacts on pastures of elevated CO2, AgResearch has been running for the past 20 years an experiment utilising a technique called free Air CO2 Enrichment, or FACE. The reason we need free air CO2 enrichment, and I'll show you how it works in a minute, is basically if you put a cover on any vegetation or plant, you're changing the environment through blocking out certain radiation, there's no wind, etc., etc. So this technique enables you to grow, in this case pastures, under relatively realistic situations with only changing the CO2. So how does a FACE system work? We have an area of pasture in this case, which is about 100 square metres. It's a 12-metre diameter ring, we call it, which is surrounded on the outside by standpipes. Those standpipes are joined up together with an underground pipe which carries CO2 from a big CO2 tank. Those standpipes also have valves inside them, and we basically monitor the CO2 level in the centre, as well as the wind speed and the wind direction. If the wind is blowing from this direction, the valves in the upwind standpipes, which I've indicated there, will emit CO2. The other valves are all shut. Every 2 seconds, that information about CO2 level and the wind speed and direction is updated, and the computer will analyse the situation. If the wind changes direction, those first set will close and this new set will open and the CO2 blows across the ring. So over the course of a day, a month, a year, we're aiming for a CO2 level of about 500 ppm, well, not about, the target is 500 ppm. So ambient levels at the moment are about 400. So we're going for about CO2 levels at current emission trajectories of about 30 years' time, I think, 40 years' time. So inside this ring, we conduct our experiments. We graze it as a farmer would graze periodically. So rotational grazing, we sample vegetation, we sample the soil. So a raft of experiments are done within this experiment. There's a number of these FACE experiments in the world on crops, rice, wheat, forests even, but this is the only one that's on pasture using actual grazing. So it's quite a unique experiment. So some key results from what we found. Increased pasture production, about 10%. But not always. So if you've got a drought, obviously nothing's going to grow, so you don't have a response. But it does change. It has changed over the course of the experiment. We've had changes in the species in the pasture. So the pasture the species that are in the pasture. There's about 20 species in there, but some species have benefited more from the CO2, but then they cycle back. It's quite a complicated system. We've also had changes in the soil nutrient cycling, as well as the suggestion of changes in animal intake and methane production. So what we've done is taken the data from the FACE experiment and used it to parameterize a pasture computer simulation model called APSIM for elevated CO2. It's quite hard to get a picture of a model, but there's a screenshot of APSIM in action. And what we basically did was run APSIM with global change projections for future CO2 and climate for different regions of New Zealand, which have different soil types, and we generate potential future pasture growth curve rates, pasture growth curves. I'll talk a bit more about pasture growth curves in a minute, but those pasture growth curves were put into an economic farm system model to determine not only the impacts in the future of global change, but also any changes we can make to the farm system which may mitigate or even take advantage of global change. So for example, here we have the Hawke's Bay. The solid line is now, so this is months at the bottom, and your pasture growth rate on the side. For those who are not familiar with pasture growth curves, basically how many times do you have to mow your lawn in a month? Okay, so in winter, maybe once a month if you're lucky, spring, and then autumn and winter again. So the solid line is now, and the dashed line is an average curve for 2040. So you'll note that the peak in spring is a little bit higher. But what we're missing here is this sort of summer shoulder. So if you're a farmer, your whole system has got to change. So you might want to take advantage of this spring peak by having greater lamb numbers or increasing your lambing percentage. You want to maybe make sure you're not stuck in here by getting rid of your lambs earlier. So you can tweak your system to either not have any effects of climate change or take advantage of it. So like I said, we took those pasture growth curves and put them into a farm system economic model called FarmX. And here these black dots are individual years on a 20-year time slice from 1990 in this case here, and the white line is the median gross margin. So basically how much money you're getting off a hectare. And under current conditions for this particular system, we're getting just under $500 a hectare of gross margin. If we didn't do anything to our farm system and left it the way it was, and we put that future pasture growth curve in there, we dropped to about $250. Our gross margin would be halved. We then decided, well, we'll have a bit of a play around with our lambing dates and our weight gain for the lambs, what have you. And in this particular case, we were able to bring our gross margin back to what it is now under these projections. One interesting thing we did as part of the study was looked at, there's a concept called climate analogues. So what they do is they take farmers from Malawi and they put the climate change scenarios into the climate, and in 50 years' time, what will Malawi look like? And it might look like the South Sudan, I don't know. And so they take farmers from Malawi to South Sudan and have a look at the farming systems that are going on there. And we did the same with these pasture growth curves. So we did Southland, and it looked more like Manawatu, for example, in the future. Hawke's Bay, we couldn't find any analogue in New Zealand. The closest was northern New South Wales on the whatever tablelands up there. So it's just, yeah, it's quite an interesting exercise to, in the future. You know, there's no farming systems that we currently have in New Zealand that could do this. So the implications of this research is that it gives us an insight into potential impacts of global change on New Zealand pastoral agriculture. Using the FACE experiment, we can test whether current technologies such as plant germplasm we have at the moment will be viable in the future, and we can also test new technologies for their effectiveness. And finally, by modelling these pastoral farm systems, we can not only determine the potential impacts on the economic viability, but also explore long-term management options to future-proof farming systems. Thank you very much.